All right, thanks guys for joining us for Dive into DSL, Digital Response Analysis with Elasticsearch. You're either in this room because you are an Elasticsearch fan, or you're probably saving a seat for the talk on how money is paid for tickets for Derbycon that's coming up. Let's start that. So before we get started, I just wanted to honor a friend and coworker of ours, Ken Johnson. Ken passed away this past year in a tragic car accident, and he was honored at the SANS DFIR Summit. And starting next year, there will be a scholarship in his honor for some new, young, and up-and-coming DFIR candidate. And they will get to go to the DFIR Summit for free, as well as attend a class. I don't have a URL for that, but just keep watching SANS, and there'll be more information on that for next year. So my name is Brian Marks, and this is Andrea Sancho. We're both senior associates with KPMG. We do forensic consulting for them. Go ahead and start off.
Yeah, so
Here's the mic.
We're going to make some assumptions because we only have 20 minutes. So we're going to assume you already have Elasticsearch deployed, and you already have artifacts parts like prefetch, link files, MFT, all that into field value pairs. And there's a lot of tools and talks, videos, documentation for that. So we're not gonna cover that. But what we need is the Elasticsearch DSL library for Python. Here's the command just to grab it. Go ahead.
So a little bit of background on the Elasticsearch DSL and what makes it different from the Elasticsearch library is, well, first of all, the functionality in this. We're going to be using Python, but the same functionality is available in Ruby, Java, .NET, and PHP. DSL has a bunch of different objects. We're primarily going to be using query, aggregation, and search. And the coolest thing about the Elasticsearch DSL is that you can combine query objects with Boolean operators, like these up here. These DSL objects can also be deserialized to a Python dictionary. And if there's any non-coders out there that are a bit confused on deserialize or whatever, we'll cover that. It's just like printing out to a string. Queries support any Elasticsearch query type. We're going to be using query string, and if you use Kibana, then you've used query strings. So another thing to mention about Elasticsearch DSL, I went to Elasticon and I was able to meet Hansa Kral. He's the developer of the Elasticsearch DSL. He's also the developer of the Elasticsearch Python library, and he's also a core Django developer. So if you do use Elasticsearch DSL, don't be surprised if it plugs in beautifully with your web apps in Python. So we're going to make an example query with the Elasticsearch DSL. So you would import the big Q object for query from the Elasticsearch DSL. And let's say we want to build a query to find evidence that a file executed. Great artifact is prefetch. So all we do is build our query, artifact type prefetch, and then now we can deserialize it to a dictionary. This is what that output looks like, and it's pretty straightforward. Just a couple curly brackets, JSON for that query. So let's get a bit more complex with this and take that same query, but let's say we also want to look for amcache artifacts. Let's say this is Windows 8 and above machine. Maybe prefetch isn't enabled, but we do have the amcache. We want to look in both places. So we just build an additional query, and then we can combine these two with the OR operator. So this query would be artifact type prefetch or artifact type amcache. Again, we deserialize it to a dictionary, and this is the output that we get. This is a Elasticsearch REST API body file that you would send whenever you're searching with Kibana. This is actually what gets sent in the background, and this, if you made this type of query, this is the output that you would need for that body file. I have seen in code and presentations people doing it this way on the right with string substitutions. They have essentially an OR Boolean operator query, and then they just use string substitutions. There is an easier way. The Elasticsearch DSL, this is why it was created. You can see this starts getting bit more complicated with square brackets, curly brackets. If you miss one of those, if you miss one comma, it will not work. So this definitely makes your life easier. So let's make this even more complex. We're going to go into our third version of this query. Let's say with the AM cache also has all the DLLs that were loaded with an executable. Let's say we just want to filter those out, just look at the executables. You can use this tilde, this curly tilde, in front of the queue as a Boolean not. So if we build this last query, this would be artifact type prefetch or artifact type and cache and not path ending in DLL, all in that query right there. We deserialize it to a dictionary. You guys probably can't see this, really small font, could barely fit onto the presentation, but that's my point. So whenever I first made one of these complex queries, I was just adding a couple together, but then started going with it and making a lot more complex ones. It kind of struck me, this looks a bit like a Yara signature. If anyone's done any binary static analysis, Yara is a language that you can use just basic logic queries to do static analysis on binaries. So we were thinking in the lab that we needed some way like this to query forensic artifacts. And so with this, we came up with a signature of forensics using Elasticsearch DSL with this query logic. So if you have things like Yara and IOCs for those use cases, what do we have for our use case of signature forensics? Well, we have all the features of Apache Lucene syntax that is built in with the query string. That's Boolean operators in the search string, as well as wildcard queries, that you guys know wildcards. Phrase queries is just a string of words, but the coolest thing is you can do proximity queries on those phrase queries to find matches within a word or two. You can also use fuzzy queries to find iterations of SVC host with a 0. This uses the Levenstein distance to find the difference in letters in a word. Range queries, there's a query to find all user activity in Windows event logs, all in one little search. Regular expression, where would we be without regular expression? We would be hard coding file paths. So this will match on both 32-bit and 64-bit program files directory, just as one use case, as well as what we covered in the previous slides on the query objects. So, and since we have this in that query string, potentially you could reverse that back to a Kibana search string if you want to look at it in there, make some visualizations. You could get it right back into that format. So now that we have those queries, Andrea is going to show some really cool stuff we can do with those queries and aggregations.
Hi. So let's talk about aggregations. What are aggregations? Aggregations are analytics that are built at search time. You don't get the data, the whole document indexed in Elasticsearch back from it. You just get the counts, the aggregations built on them. They build buckets based on the match criteria that you specify for your aggregation. And there's so many types of aggregations. Here are some examples. We're going to cover a few of them. But every new version of Elasticsearch, they just launch new aggregations and new formats, which is really cool. But the best part of all these is that you can nest aggregations. And there's no limit on how many child buckets you can build out of an aggregation. So let's build one. How do we do that? We create the query. Brian already covered that pretty much. Here we're going to select all the MFT entries that we have ingested previously in Elasticsearch. So we use select type MFT. Then we're going to create the aggregation. This is going to be the parent one, the basic aggregation that is going to be inserted in our search. So we import the capital A object from the Elasticsearch DSL, and we are going to build a terms aggregations. That's going to be matching an exact term that we specify. And on the field that we specify, we use the extension from the MFT file entry that we have ingested. Then we just have to add that to our search object. The search object is using our ES client, the Elasticsearch client. And we just have to add our query, which is all the MFT entries, and then the aggregation, the top level bucket, which we're going to define here the name that we're going to give it. We need that name later for printing out that aggregation and accessing the results. Our name is extensions. It just makes sense. And we just execute our search. And Elasticsearch returns everything, both the query results and the aggregation in that result object. So we can answer questions like that one. How many different files are on a file system per file extension? So this is how you access the aggregation object. You just get the result object, go to the aggregations, and then the extensions, which is the name that we declare for aggregation, and then you print all the items in the bucket. This sounds pretty complicated, but in my mind it works just like this. That's the name of the aggregation, and then you have all the MFT entries, and you find one entry which extension is HTML, you create a bucket and put that inside. Then a PNG, DLL, and so on. And you just have all the counts of all the file extensions on the MFT. Let's nest an aggregation and answer a more complicated question. How many files are created on a daily basis on a file system? So now we have, again, the query with all the MFTs. And now we are going to have an aggregation of type date histogram. Instead of the term ones, our parent aggregation is going to be a date histogram based on the creation date of that MFT entry. And for that, and after that, we create a tile on that parent aggregation, and that is going to be a terms aggregation based on the file extension on the MFT entry. We add our query to the search again, and we add our top-level aggregation to the search object. You don't need to add the tile. The tile is embedded in the parent aggregation. We execute our search, and here's what we get back. All the files that have been created per file extension per day on a file system. And if you guys are familiar with forensics, there's something really particularly odd in this slide. And yeah.
So actually, this is from real data that we were investigation that another coworker of us was working on, and we needed some test data. So we ran this, and we were just looking, and it caught our eye that there's a bunch of 81, 82, 83 files on that system that he's investigating, and it was on New Year's Day. And so we grabbed him and we said, "Wow, you're working pretty hard on New Year's Day, on this." And he said, No, I was with my family. Why? And we showed him this, and he said, "Oh, that engagement started like the second week of January. That client paid another firm to come in, and they did collections and then no analysis, and then just handed the guys a bill, and then they called us." And so I said, "Well, I guess I hope you didn't have to carve any files or anything like that, because they just performed a logical acquisition on the hard drive that we could see on there." So, thanks first responders. Appreciate that.
Yeah, so we can keep nesting aggregations and answer more complex questions. Like, for example, this is a good one. How many users log into the system per day? Which user accounts and one logon type? So to build that, we're just going to get all the Windows event logs that we have ingested previously on Elasticsearch, and we're going to query on the event 4624. Then we're going to add a date histogram per date. That's the event date. And to that, we're going to create a sub-bucket, a child bucket, based on the username. And to that, we're going to create a third sub-bucket based on the term logon type. And then we're going to execute. This is how, like, on the right, you see how the buckets will be built. Each aggregation will generate its own child buckets, but you don't get more data than what the counts are on those buckets. And then we add our query to our search, we add our aggregation to our search, and we execute our search. And this is what you get back. This is the SANS spoiler alert. This is from SANS 508, I think. This is the total logons per day, per username, and per logon type. That can provide you a lot of insight when you're starting an investigation and you don't know what to look for first. Also, another cool thing about these aggregations, if you've used Kibana, what does in the backend is just that. It's aggregations. They aggregate and they just put pretty colors and areas and shapes to it, and you can see things really spot the needle in the hay really fast. So here we have what the aggregation that we just did with the user logons per system, per logon type, username, and day is just that. Is every per day, like the x-axis will be the time range, and then we have the logon types and the usernames. So each of those graphs is a username, and then the colors are logon types. I don't know if you guys can see it, but yeah, that's it. So what does all mean?
So I think you guys can kind of see what we're doing. We kind of abstracted a higher level language of forensics, and then with our forensic artifacts that we ingested into Elasticsearch, this enabled us to automate the easy things in forensics. Whenever We have an investigation to have pre-stored queries. And if a new artifact comes up, it's great because this is scalable, that you can just add on to that query of all the program execution that we have. If all of a sudden in Windows 10 we have a new artifact, you just add on another query to that big query and just keep going. This also made us more consistent among analysts because we all have access to all the logic that we're looking for whenever we start to investigate a case. It's not just dependent on what you learned at SANS or some other training. We also do a more rigorous investigation that, let's say prefetch isn't enabled and that's the only thing that someone was going to check for file execution. We have almost like 10 other artifacts that we check if those are there, as well as preset queries for like anti-forensics to check if the event logs were clear. Maybe not every investigation you check that event logs were cleared. And we also ingest everything from volume shadow copies. So we're talking lots and lots of data, and it's really nice to have it in Elasticsearch because it's really, really fast, and we can cut through millions and millions of lines really quick to in our forensic investigations.
And it's free?
Yeah, it's free, it scales, it's fast, and we've also used this in investigations that involve more than one host. So in Elasticsearch, you have an index that we typically do one host per index, but let's say there are 3 involved in an investigation, maybe there's possibly lateral movement. You can create an alias in Elasticsearch, which is essentially a pointer to those different indices, and then query on that alias, and then see program execution across all 3 machines in the same normalized timeline. So thank you guys for attending. Do we have any questions? Yes.
So how are you handling authentication?
So whenever we're processing this, there's no authentication. We're running this all locally. So yeah, we're not going from a remote host authenticating.
It's all in the lab environment. It's closed down. There's no access from the internet. So because this is evidence, this is like highly sensitive, confidential data. We don't want anyone accessing that. So we just decided to cut every access to it from the outside.
But if you do use, I believe, Elasticsearch Shield, you could build that in with Elasticsearch DSL. We'll work with authentication if you need it. Thanks, guys.
Thank you.
Thank you.